Hello everyone, wishing you all a very good afternoon. I hope all of you are fine. Am I audible and visible to all of you? Can you see me? Can you hear me? Please raise your hand so that I know that I'm audible and visible. Okay, great. Now, in this class, we'll try to wrap up this pending topic of electrostatics. And from the next class, we'll probably move on to capacitance. In this class, we'll try to deal with dipole and Gauss law, and we'll see what sort of problems you can expect in the examination hall. I remember I told you to at least go through uh, the topic of dipole. Have you gone through what is the electric dipole? Have you seen that part? Electric dipole? Anyone? I'll quickly go through it if you have not seen it. So, what is an electric dipole? Electric dipole is nothing but a combination of two charges equal in magnitude but opposite in sign, separated by a small distance. This distance A should be very small compared to the distance of any point that we are talking about. So, this combination becomes a dipole. So if I have a plus q charge and a minus q charge separated by a small distance, this combination is a dipole. Every dipole is characterized by something known as a dipole moment. A dipole moment is a vector quantity, and the value of that dipole moment is A multiplied by Q, where A is the length of the dipole. Some people also call it dipole axis, and Q is the value of one of the charge. Remember, the dipole moment is always directed from the negative charge to the positive charge. So you might have a simple question like this, where you have a triangle, you have a plus Q charge here, you have a uh, minus 2Q charge here, and you have a plus Q charge here. And then you are supposed to find out what is the dipole moment of the system. How do you find the dipole moment of such a question? These question can come. So assume that this is plus q, and here it is 1 is minus q, and here it's plus q and 1 is minus q. So you have one dipole moment p1 like this, one dipole moment p2 like this. P1 and P2 are two vectors which are inclined at some angle. You can find the value of the resultant vector, and you can find out the net dipole moment of the system. This is an easy question. You can expect such questions sometimes in the JEE. So I've told you, if this question comes, you should be able to solve it like this. Yes or no? You understand this? Then we have the usual formula for electric field due to a dipole and an axial point. This is the actual formula for electric field. This one is the actual formula for the electric field. 2q kq into 2ra. This 2ra becomes the dipole moment. 2r into q becomes the 2a into q becomes the dipole moment. So you can write this formula like this: k into a, k into r into dipole moment p divided by r square minus a square by 4 raised to the power of 2. This is the original formula written in terms of the dipole moment. I've written 2aq as a dipole moment. The length of the dipole is a, so it becomes q into a. Q into a becomes the dipole moment. Sorry for the mistake. Now you have a shortcut formula when this r, the distance is very large compared to a. So this entire term can be neglected, and you have this formula 2kp vector divided by r cube. Now this is a vector formula for electric field. The direction of this electric field will be same as the direction of dipole moment. The direction of dipole moment will be from negative to the positive charge. So please remember this. Now, if you come to the other formula of electric field at the perpendicular bisector or the equatorial position, as you can see, the dipole moment P is like this, but the electric field will be like this. So electric field will be in the opposite direction, that is given by this negative sign. This is the actual formula of electric field if R and A are comparable. This is the formula when R is, the distance is very large compared to dipole axis, and this becomes the shortcut formula. The shortcut formula can also be written in this fashion. Equatorial is minus k p by r cube. Looking at the equatorial and the actual one, you can say E actual is minus 2 times E equatorial. But remember, you can write these equations vectorly. E axial is always in the direction of P vector, and E equatorial is always in the direction which is opposite to that of P vector. Do we understand this? All of us remember this? All of us remember this? Can I have some reason that we understand this? Okay. Now, if I have a general point, and this is a general point here, point A, and you have the dipole moment like this P, and this angle is theta. Remember these terms. What I can do to find the electric field at this point, I can break this dipole into two dipole. One is like this, P cos theta. One is like this, P sin theta. For P cos theta, it becomes an axial point. So the field becomes 2k into P cos theta by r cube. For this P sin theta dipole, this becomes a point on the perpendicular bisector, and hence the electric field becomes k into P sin theta by r cube. This is a very nice way of getting the electric field of this dipole at any general point. I think this method is given in your CBSE textbook. Now these two fields will be perpendicular to each other, and you can get the value of the net field by adding up in terms of square ER square plus ET square under root. So your net electric field will be like this. It will be making an angle phi with your R vector. Here is your R vector. It will make an angle phi with this. Tan of this phi will be equal to tan theta by 2, where what is theta? Theta is the angle. See, theta is the angle that this point, the radius vector makes with the r vector. The radius vector makes with the dipole axis, that is theta, and this is phi, and this is your E net. Do we understand this, all of you? This is how you can find the electric field at any general point of this dipole. On similar lines, you can get the formula for electric potential due to a small dipole. This is the actual formula. You have to remember this. This is the approximate formula. If R is very, very large compared to A, this is potential at an axial position. And if you look at the potential at equatorial position, the potential will be zero. Why it will be zero? Because whatever positive potential, positive charge creates, the negative charge creates the same potential but in the negative sense, and hence the net potential becomes zero. If you want to find the potential at any general point, and please write this formula very, very carefully. So this is the electric potential at any general point. It is k times p dot r divided by r q vector. I have enhanced it. You may not find this formula in other books, so please have a look at this formula. What is P? P is the dipole moment. What is R? R is the radius vector, and this is how this formula looks like. If you want to find the electric potential at the point A. This is my R vector. You take the dot product of P with R and divided it by the R ka magnitude cube. Do we understand this? You may not find this formula in other books, beta. Please have a look at this. Am I clear? Am I clear? Can I have some reason that we understand this formula? This is the formula, general formula for electric potential due to a dipole at any point A. Remember, we have always taken potential at infinity to be zero. That is the only way by which we can find the potential of any other point. Now, apart from this, what all questions can come will be of a dipole in a uniform electric field. If you place the dipole in a uniform electric field, as you can see, the net force will be zero in all cases, because in all cases the force on the positive charge will be along the direction of field. In all cases the force on the negative charge will be opposite to the direction of electric field. So the net force in all the cases will be zero, whether you keep it like this or like this or like this. But net torque may or may not be zero. As you see in this case, if it is kept at an angle theta, the net torque is not zero. Force are cancelling each other out, but the torque of both the forces are adding up, and adding up in such a way that will try to bring the particle back to its original position. This is the condition of stable equilibrium. It will execute simple harmonic motion for small amplitudes. It will be simple harmonic. The torque will be given by P cross E. Now this P cross E torque will be used in that magnetic loop wala case, current carrying loop placed in a magnetic field. It will also experience torque. It will not experience force on that magnetic loop. Current carrying loop will be zero, but torque will be M cross B, where M will be the magnetic dipole moment and E would be the electric field here, magnetic field there. I can write the magnitude of this torque as P into E into sine theta. It depends on the value of sine theta. If theta is zero, that is the condition of stable equilibrium. Torque is zero. If theta is 90, torque is maximum. If theta is 180 degrees, that is the condition of unstable equilibrium, when electric field and dipole axis, dipole moment are in the opposite direction. If you disturb it from that position, it will never come back to its original position. It will come back to the position of stable equilibrium. Do we all understand this? Yes or no? Can I have some raise hand that we understand this, sir? Theta is equal to 0 is the position of stable equilibrium. Theta is equal to 180 is the position of unstable equilibrium. And then you can have a question like this. Am I audible and visible to all of you? Can you see me? Yes, I mean, I'm not able to. You can see me? My Zoom. Okay, I think I'm audible and visible now. There was some lag there. Okay, now you can have a question of this nature, which is example number 49, 89. A dipole is formed by 2 point charges plus q and minus q. Mass m are connected by a rod of length L and mass m. This dipole is placed in a uniform electric field. If the dipole get disturbed a small angle from the stable position, prove that the motion is simple harmonic. So how will you prove that the motion is simple harmonic? Anyone? How will I prove that this motion is simple harmonic? Anyone? So I already know that torque is minus P sine theta. For small angles, you can call it minus P. Minus only indicates that if you rotate it like this, it will be like this. If you rotate it like this, it will be like this. So it is a restoring torque. That torque must be equal to the total moment of inertia multiplied. This torque will be equal to total moment of inertia multiplied by alpha. From here you can find the value of alpha, and if you can show that alpha is minus omega square times theta, whatever is the constant becomes omega. From there you can find time period is 2 pi by omega, and this is what they have done. Moment of inertia It will be rotating about a center of mass. So you have to find the moment of inertia of the entire system about the center of mass. The first one is the moment of inertia of the rod. The second one is the moment of inertia of the two charges. Multiplied it by 2 because there are two charges. We found the moment of inertia, and from there you have calculated the time period of oscillation of this block. Do we understand this? Or have I gone too fast? Torque is P cross E, minus sign indicating that it is opposite to the direction of angle theta. For small angles, theta becomes sine theta or sine theta becomes theta, and we equate it to I alpha. I is the total moment of inertia of the system. Can I have some reason that we understand this so that I can move forward? From there, you can find the value of omega. Once you get the value of omega, you should be able to find the time period, potential energy of a dipole in a magnetic field. It is very simply given by this formula. Which formula? This one. Energy of the dipole in a magnetic field or electric field. In electric field, it will be a dipole consisting of two charges. In magnetic field, it could be a magnet or it could be a current carrying wire. Both the cases answer are same. Electric field, the answer is minus P dot E. Magnetic field, the answer is minus m dot b. Theta is 0. When theta is 0, energy is minimum, and therefore it is the condition of stable equilibrium. Theta 180 maximum, it is the condition of unstable equilibrium. This is the graph between u and theta. Minimum energy, maximum stability, maximum energy, minimum stability, minimum energy, maximum stability. So the downward are the 2 points of stable equilibrium, else the upper points are points of unstable equilibrium. Do we understand this? Can I have raised hand that we understand this, sir? We are doing problems in dipole mm, moment. I guess that there could be a problem this year on this dipole. That's why I'm insisting so much. Now here is a simple problem. 2 point masses m and equal and opposite charge of magnitude q are attached to the corners of a non-conducting uniform rod of mass m, and the system is released from rest in uniform electric field as shown. Theta is 53 degrees. Find the angular acceleration of the rod just after releasing. So it's a question of rotation. Number two, what will be the angular velocity of rod when it passes through stable equilibrium? So it is a question of rotational kinetic energy. Number three, find the work done to rotate the system by 180 degrees. So it becomes a question of electrostatics as well. All the three things coming here. So I think this is a good question. I'll give you 2 minutes, solve it. The first part is finding out the angular acceleration. How do you find the angular acceleration? You find out the torque. Torque is P cross E, P into E into sine theta. Sine theta is 53 is equal to I alpha. I is the moment of inertia of this system. You can easily calculate the moment of inertia of this rod and this system. One is ml square by 12 about the center. Other is 2m into L by 2 whole square. To find out the moment of inertia, you should be able to find out the value of alpha, and this is the value of alpha. Everyone got this answer? Yes or no? Please raise your hands. Torque is equal to I alpha. Great, Vishnu. That takes us to the second part. Whenever you ask velocity or angular velocity, that is an indication that this question has to be done by work energy theorem. Energy is conserved. Total kinetic energy or total mechanical energy at point 1 will be equal to total mechanical energy at point 2. At point 1, you only have potential energy and no kinetic energy minus P dot E. At point 2, you have kinetic energy as well as potential energy minus P dot E. Here it is minus P into E into cos of 0, and kinetic energy is half mv square. Put the value of I and from there you will get the value of omega. What is the work done by the external force? Everyone knows that it is final energy minus initial energy. Work done by all forces equal to change in kinetic energy. You can put that formula and you can get the answer very, very simple. Do we get this? Yes or no? Here they have calculated the work done by external forces. So when they've asked this question, what do you understand? You must understand. Find the work done to rotate the system by 180 degree. When they say that, what they mean is you are going to rotate it very, 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 very slowly. So work done by all forces must be equal to zero. So work done by external forces plus work done by electrostatic forces must be equal to zero, and therefore work done by external forces will be negative of work done by the electrostatic forces, and that is how they have found out the work done by external forces. Please remember this. Please remember this. Now, this is one topic that you might not have studied in your regular class. I'll just go through them. Dipole in a non-uniform electric field. If it is a uniform electric field, the force in all the cases is zero. But if it is a non-uniform field, the force will not be zero, because if the electric field is non-uniform, electric field at the positive charge and electric field at the negative charge may not be same. So there will be a net force on the dipole, and the net force on dipole will be given by this formula: P dipole moment into d E by dx. Just remember this. This is not the exact formula, but I will not get you the exact one because it might just confuse you. So in your cases, it will be P into dE by dx, where dE by dx is the derivative of E with respect to the dipole axis. Do we understand this? Do we understand this formula? Please remember this formula. Please remember this formula, because this formula is going to be like a SOS for you. SOS meaning save our souls. And you can apply this formula here in this question. Someone asked me how the, please send me message Teja on the other one. How m by 2 into 2, 2 times, that is you are talking about the moment of inertia. That is the moment of inertia of the two charges about the center of mass. One charge is m, the other charge is m. The one mass is m, other mass is m. So you are talking about the moment of inertia of the two charges. One is m, one is m. The moment of inertia of this will be m into L by 2 ka square. Moment of inertia of this will be m into L by 2 ka square. You add, you get 2 m L by 2 ka square added to the moment of inertia of the rod. Do we understand this better? Now you have this ring of charge Q, radius R, and you have a dipole. This is the type of question you can encounter in your JEE Advanced. Please have a look. A short dipole is placed on the axis of a uniformly charged ring at a distance r by root 2 from the center. Find the force on the dipole due to the ring. I'll give you a minute to win it. A minute to solve it. Anyone can do this? So how you got to do this? You have to use, remember I told you, you'll have to use this electric field by this ring and by this. You don't remember them? You will take a lot of time to solve this question. You will not be able to solve it. So it is P into dE by dx. P is the dipole moment. It's already given to you. P dE by dx. You have to find the derivative of this with respect to x and put the value of x as r by root 2. If you get the answer as 0, the force acting on this dipole is 0. In this case, we are getting the answer as 0. That is why the answer is. Do we understand this? Am I clear how we have applied this? Can I have some raise hand that we understand this? Okay. Then you can have various cases where you have the force between a dipole and a point charge. How will you find the force on the dipole due to the point charge? So you can do either one of them. Either you can find the force on dipole due to the point charge or point charge due to the dipole. The easier one will be to find the force on the point charge due to the dipole. You can easily use the electric field due to the dipole. You can find the force on the charge due to dipole, and this is an action reaction pair. So force on electric dipole due to the charge will be opposite of this. So this is a shortcut way of getting your answer of electric force on dipole because of the charge. Are you getting my point how we are doing this? Two way around. Instead of finding the force on dipole due to the charge, I found out the force on charge due to the dipole. Do we understand this, everyone? Do we understand this, everyone? Then we have force between two dipoles. Force between two dipoles or force between a charge and a dipole when the configuration has changed. In the first case, the configuration was like this. The charge and the dipole were along the same axis. In the second question, it is like this. Find the force on the charge due to the dipole. Again, you can do it in the same way. You can find the electric field due to the charge. Instead of finding the force on charge due to the dipole, it is easier to find the force on dipole due to the charge, right? So find the electric field due to the dipole on the charge and find the force from there on. Do we understand this? How we have done this? Do all of us understand this? So whenever you get a question of electric force between a dipole and a charge, what you got to do is find the force on charge due to the dipole, and that will give you quicker answer. Now, in rare circumstances, you might have a question where there are two dipoles. Force on charge dipole P2 due to short dipole P1. They are placed at a distance r apart. So what do? You find the force on the second dipole, you multiply the dipole moment of the second one by the derivative of electric field with respect to r. You find the electric field with respect to r and differentiate it, and that will be your answer. Please remember this. If you can't do this, you can remember this. Remember the configuration here. Remember the configuration here. The configuration here is like this, beta. Both the dipoles are placed along the same line. In that case, the answer is minus 6 times K E1 E2 by R raised to the power 4. Can I have some reason that we understand this, sir? Now, The last question in this configuration will be like this. One dipole placed like this, the other dipole placed like this. One dipole like this, other dipole like this. Now, instead of going to this entire thing, you can just use this formula. And you can get your answer. In this case, the answer would be like this. So when both the dipoles are placed like this, the formula becomes half of the actual formula, actual answer that we got in the first case. So this will encompass everything that can be asked on dipole in your JEE Advanced. You cannot have a question. If it comes from dipole, it cannot come from anywhere else. I have taught you everything that was supposed to be known. Do we understand this? Can I have some raise hand? That dipole is clear now? Raise hand will give me more confidence that you have understood this. Right? That takes us to electric flux, and we'll just go through what is electric lines of force. It's an imaginary line drawn in such a way that the tangent drawn at any point gives us the direction of electric field or electric force. From a positive charge, they are moving away. From a negative charge, they are moving towards. If it is a point charge, they are directed radially outwards. If a point negative charge, they are directed radially inwards. You must be knowing it. Two point of force cannot cut, cross, or intersect. They are in open loops. They do not form a closed loop. They start from a positive charge and end on a negative charge. They cannot be a closed loop like this. Do we understand this? The number of lines per unit area, the number of electric field lines per unit area is basic to electric field intensity E. More number of field lines means more electric field. Less number of electric field lines means less number of electric field. We all know this, yes or no? And this number of electric field lines is primarily proportional to charges. If there are more, the charge ka value is more number of field lines will go out. The charge is less, less number of field lines will come in or go out. Electric lines of force or start or end from the surface of a conductor. It is always perpendicular. If it is a negative surface, they will end perpendicularly. If it is a positive surface, they will emerge out perpendicularly. They always end or emerge perpendicularly. They will never move across the conductor. Inside the conductor, electric field is always zero. Do we know this? Can I have raised hand that we understand this? Yes or no? Okay, I'll move forward. Then we move on to electric flux. The number of electric field lines per unit area is known as electric field intensity or electric field strength. The total number of electric field lines which are passing perpendicular to the area is known as electric flux, denoted by the letter phi. It is a scalar quantity. How do you find the electric flux? It will be E dot ds ka integral. It is the integral of E dot ds. If I put this sign, it is integral over a closed surface. If I do not put this sign, it is integral over a open surface. What do you mean by a closed surface? What do you mean by open surface? Integral like this, integral over closed surface, integral like this, integral over open surface. This is a closed surface. A closed surface has a volume. If I open the cap, it is an open surface. A tabletop is an open surface. A cupboard which is open, which is closed surface. A cupboard which is open surface. Do we understand open and closed surfaces? You understand open and closed surfaces? Every closed surface, every surface has an area. Area is treated as a vector quantity. How do you take the direction of area vector? If it is a closed surface, area vector is always perpendicular and it is going out. So for this surface, it is always perpendicular, it is going out. But if it is an open surface, the area vector direction is not defined. It can be inner perpendicular, it can be outer perpendicular. For a closed surface, it is always outward perpendicular. For a open surface, it can be inward, it can be outward. So for a open surface, area vector will always be given to you If the area vector here is like this, then electric fields are going out. If the area vector is like this, then electric fields are coming in. Inward, incoming electric field, inward flux is negative, outward flux is positive. And if the angle between electric field and area vector, in this case, area vector is coming out or going in, the area vector and angle, the angle between area vector and electric field is 90 degrees. In that case, the flux would be zero. Electric flux can be positive, can be negative, depending on the angle. If the electric field is like this, area vector is here, it is positive. Area vector is here, it is zero. Area vector is here, it is negative. Area vector is here, negative maximum. Area vector here, negative. Area vector here, 90. Area vector here, positive. So all these cases where the angle is acute, it becomes positive flux. All the places where angle is obtuse, it becomes negative flux. If the angle is 90 or 270, flux becomes zero. Do we understand this? Yes or no? Have I gone too fast? I hope you understand the meaning of electric flux. Scalar quantity can be positive, can be negative, depending on the angle. Incoming is negative, outgoing is positive. Same thing for magnetic flux. And when magnetic flux changes with time, you have electromagnetic induction. That will be the last chapter in this category of electromagnetism. Solved examples, you have to solve example number 100. It's a very simple question. Electric field is given by this vector form. E naught key value is given. Find the flux through a rectangular surface of area 0.2 meter square parallel to YZ plane. YZ plane, it is parallel to YZ plane. So area vector will go along x-axis. You can take it as positive x-axis. You can take it as negative x-axis because positive and negative are not defined here. So either you will get answer as positive something or you will get answer as negative something. You'll have to take the dot product. I hope you can get the answer for this one. So I think you got the answer. You have to do E dot ds. You can do the dot product. You can get the answer. Similar question, charge is placed here. What is the flux through this surface? This surface is like this. Electric field lines will be going along the surface. So the flux would be zero. What is the electric flux through this? So you have to integrate it like this. Electric field lines are going like this. Area vector is going like this. So you have to find this angle, find the small flux and integrate it for the entire ring or disk. You will be able to find out the flux created by this flux passing through this ring because of this charge. Now the same question could be asked in a different way. For example, you have a cylinder, the length of the cylinder will be given to you, and then you have a charge placed at the center of the cylinder, and you would be asked to find out the flux through the curved part of the cylinder. How will you find the curve? How will you find the flux through the curved part of the cylinder? Now, this is not a direct question. If you try to do it directly, you can do it, but it will take a lot of time. You can do it in indirect way. How do you do it in indirect way? If you close these two ends, it becomes a closed surface. Then you can apply Gauss law. The total flux will be total charge divided by epsilon naught. That will be the total flux. The charge is Q. Then from this total flux, you can subtract the flux which is going through this circle. You can find it out by putting the value of x here, L by 2. One more area is here. So you multiply it by 2. From the total flux, if you subtract 2 times of this flux, you will get the value of flux through the curved part of the cylinder. Do we understand what I've told you that right now? So remember, whenever you get a question like this, this is the way you do it. For example, this question could be in this way. This I could put the question in this way. For example, this could be a elliptical surface. This could be an elliptical surface, and then I have placed the charge somewhere on this elliptical on the axis of this surface. Inside this surface, charge q. Then I ask you to find out what is the flux through this curved part. What do? You enclose it, make it a closed surface. Total flux will be q by epsilon naught. Subtract the flux of this circular part, which will be given by this formula. Remember this formula. Subtract it from the total q by epsilon naught, and you will get your final answer. Do we understand this? Any question of this matter have to be done in this way. Got it? Similar thing has been done here. Remember, whenever you have a uniform electric field and you have a closed surface, if I have this closed surface and I place it in a uniform electric field, what will happen? Whatever number of lines of field go in, the same number of lines of field will go out. The total flux through this entire surface will be zero. You can apply this concept and do questions like this. If I have a hemispherical shell, half hemispherical shell placed in a uniform electric field, what is the flux through this part, which is the curved part? How do you do it? You make it complete. You put a cap on this side, make it complete. Now it becomes a closed surface. What is the flux through this closed surface, which is placed in a uniform electric field? The total answer is zero, because closed surface in a uniform field, total flux is zero. Total flux is zero means whatever flux is passing through this part, the negative of that thing is passing through the curved part. Then find the flux to the curved part. It is simple. E multiplied by pi r square. This is incoming. If one is incoming, the other one would be outgoing, and you will get the answer. See, they have made it. One surface is circular. What Whatever may be the other surface, if it is a closed surface in a uniform electric field, total flux coming in will be equal to total flux going out. If someone asks you how much is the flux through this, you just find the flux through the circular part and you get your answers. Do we understand this? Can I have some reason that we understand this, sir? This is your Gauss law. Flux through any closed surface, flux through any closed surface will be equal to charge enclosed by surface divided by epsilon naught. I hope you know this law. Yes or no? Please raise your hands. Flux through any closed surface is equal to the charge enclosed by the surface divided by epsilon naught. Now, there are certain important terms, things that you must remember about the Gaussian surface of flux through a Gaussian surface of flux through a closed surface. Flux through a Gaussian surface is independent of its shape. Flux through a Gaussian surface depends only on the total charge present inside, not outside. Flux through a Gaussian surface is independent of position of charges inside. Wherever you place the charge, total flux will be same. Electric field due to at the Gaussian surface is due to all the charges present inside as well as outside. So whenever you're finding electric field using Gauss law, that electric field is due to all the charges, not only the charges inside but also the charges outside. In a closed surface, incoming flux is negative, outgoing flux is positive. If in a Gaussian surface flux is zero, that does not mean that electric field is zero. But if electric field is zero, that will mean that the flux is zero. If the flux is zero, that only means that the net charge is zero. It may not mean that the electric field is zero, but if electric field is zero, there are no field lines, there will not be any flux. Do we understand this? Can I have some reason that we understand this, sir? Okay. We can use this Gauss law, finding simple question. For example, this a point charge Q is placed at the center of a curvature of a hemisphere. Find the flux through the hemispherical surface. So what do? Create symmetry. This is one half of the cup. You keep another half of the hemispherical shell. Now the total flux through this entire hemisphere. Now this entire sphere becomes Q by epsilon naught. What is the flux through this half part? It is Q by 2 epsilon naught. This is how you can do a question of this nature, where you have a point charge Q placed here, and this distance is A by 2 and this distance is A. So what do? You put A square sheets all the way around it. So now this becomes the center of the cube, and this one side you have surrounded it by 6 sides. flux through this entire cube is q by epsilon naught. Flux through any of the side will be q by 6 epsilon naught. Do we understand this, or this is going above our heads? Now, they might ask you a question, find the flux through the hemispherical surface. One charge is kept here, other charge is kept here. How do you find it? This charge, flux through the hemispherical surface due to charge q is q by 2 epsilon naught. Flux through the hemispherical surface due to charge q, this one is 0 because whatever field lines are coming in, the same field lines will go out. Yes or no? Because if I enclose a Gaussian surface, the flux through this entire Gaussian surface will be equal to the charge enclosed divided by epsilon naught. This charge is not here. So whatever field lines are going in, same field lines will go out. And you can enclose a full sphere. The flux through the full sphere will be q by epsilon naught. Flux through half of the sphere will be q by 2 epsilon naught. This is how you can apply the understanding of Gauss law to solve problems in flux. You can also apply Gauss law to find out the electric field from this formula. If electric field is constant, we can write it as E into the area ds ka integral is equal to q by epsilon naught, and you can somehow integrate this area, find the value of this total area. You should be able to find out the electric field due to some type of charge distribution. Like for example, electric field inside a spherical shell. Inside a spherical shell, electric field will be 0 because net charge is 0. Due to a solid sphere, uniformly distributed charge, what do you do if you want to find the electric field at this point? Just find how much charge is coming inside here. I think we have done question regarding this. How much charge is here? You can find out the electric field inside, outside, everywhere. Do we remember this? Yes or no? For a line charge, for an infinite line charge, you can also find the electric field. You have to create a Gaussian surface which is cylindrical. I hope you know the theory behind it. The electric field will be 2k lambda by r. You can also, this was Gauss law. The Gauss law for electrostatics is electric integral of E dot ds is charge enclosed divided by epsilon naught. You can also make a Gauss law for gravitation. In Gauss law for gravitation, electric field will be replaced by magnetic, no, gravitational field. Gravitational field is G. You can replace mass by M. Now remember, gravitational field is always directed, so this flux is always incoming, so this is always negative. So I have written negative. What should I write in place of epsilon naught? That's my question. Minus is written because the flux is always negative. There is no flux which is going out because all the charges flux is coming in, because gravitational field is always directed towards the body, not away from the body, right? Gravitational field is always towards the body, not away from the body. What do I write in place of epsilon naught? Not G, Jayant, not G. Remember, 1 by 4 pi epsilon naught is G. So what should I write? I should write it like this, minus minus 4 pi G M, and this becomes my Gauss law for gravitation. You will not find it anywhere. Please remember this. You will not find it in any book that you have probably. Okay, so remember this. Then you have electric field due to an infinite long cylinder of volume charge density rho. What you got to do? Just apply the Gauss law. Just create a cylinder, find out how much charge is inside the cylinder, and just find the value of electric field, or for that matter, magnetic field. Rho becomes rho, r becomes r becomes r. Instead of epsilon naught, 1 by epsilon naught is 4 pi minus 4 pi g, minus only indicating the inward direction. You can get the electric field as well as gravitational field at any point inside or any point outside. Do we understand this? Can I have some raise hand that we understand this? You understand how to find it out? Okay. The last topic in this is conductor and its properties. Conductors are materials that have large number of electrons. They are always equipotential. Charges only come on the outer surface if there is a cavity. Even if you have a cavity, a conductor, and you have a cavity inside the conductor, you charge this conductor, charge will still appear on the outer surface. But if you have charge inside the cavity, then you will have charge coming on the inner surface. Electric field is always perpendicular. Electric lines of force never cross this conductor. Electric field outside the conductor is always sigma by epsilon naught. I hope you know this. When a conductor is grounded, the potential becomes zero because potential of ground is taken as zero. If an isolated conductor is grounded, then its charge will become zero, because the only way potential can become zero is by charge becoming zero. When two conductors are connected, charges will flow until the time when their potential becomes zero. Potential of ground is taken as zero, therefore the potential of the conductor becomes zero. Electric pressure, same as gravitational pressure, will be given by sigma square by 2 epsilon naught. For gravitational pressure, sigma की जगह sigma, here sigma is charge per unit area, there sigma will be mass per unit area. Here it is 2 times epsilon naught. There you have to replace epsilon naught by G. Do we understand this? Yes or no? Can I have reason that we understand this, sir? Now applying these principles, you can solve some questions of electric field, famously these questions, but I have already discussed these questions with you and we have solved them previously. How do you find the electric field at point A? You find the electric field due to charge Q, then you find the electric field due to the charge minus Q, and so on. So I think question of these types can be tackled by your own. Now, what questions can give you trouble here is a question of this nature, which I told you that you might be asked to find the charges appearing on all these surfaces. This is surface number 1, this is surface number 2, this is surface number 3, and this is surface number 4. So how do you go about this? The such a simple way is the way that is given here. You start from the leftmost sheet, call the charge as x, then the charge on the other side becomes q minus x, where q the total charge. If this is q minus x, this will be the opposite of q minus x, so it will become x minus q, because the net charge has to be zero, because the net flux has to be zero. If this is q minus x, you can write this as the total charge was given. You can find out the value of the total charge 2q. So this will become, I think, 3q minus x, so that if you add them, it becomes total as 2q. Now remember, this charge and this charge has to be same, so that will give you straight away the value of x. This charge and this charge has to be same, so x must be equal to 3q minus x. From here you can get the value of x as 3q by 2. Once you get the value of x as 3q by 2, which they have got it, then you can find the value of charges on all the sheets. Remember, facing sheets must have opposite charge. The most leftward sheet and the most rightward sheet must have the same charge. You can apply this principle. Start from the leftmost sheet, call it as x, then call the remaining charge on this sheet, then put the opposite charge on this sheet, then call the remaining charge on this sheet, then put the opposite charge on this sheet, then put the remaining charge on this sheet. This side of sheet and this side of sheet must have the same charge. With this concept, you would be able to find out any question of this nature where you are supposed to find out charges appearing on all the sheets. Am I clear with this, what we have discussed today? We have discussed starting from electric dipole, we have discussed dipole, we have discussed electric flux, electric lines of force, properties of conductor, and how to find out charges appearing on different sheets. So I'll end this class here. The next class we'll start with the topic of capacitance. We'll try to wrap it up in a class or two. Then we'll start with electric current, and then probably we'll move on to magnetic field and EMI. 5, 6 classes. I'll try to wrap it up. I hope you are finding the class interesting. If you have any doubt, you can ask me. Else, from my side, the class is over. I hope you remain safe, healthy, and happy. Bye bye.